Okay, YouTube, we've been working with numerical and variable expressions, simplifying them, evaluating them, and even writing verbal models. But now we're going to get into simplifying algebraic expressions. So these are things without numbers. This is not order of operations per se. This is more about taking something with variable terms and simplifying it even further. So we say for an expression such as 2x plus 3, we say the parts 2x and 3 are added together, or subtracted. We call these the terms of the expression. Okay, so when we talk about, say, some variable expression, we say like 2x plus 3 is our example here. We can say minus 4 squared plus 8 over sine of x. Okay, we would say each of these things that is separated by one of these pluses or minuses, or we could even rewrite them all as a plus, add a negative. But we say that these are all terms. Okay, so we say these are terms separated by pluses or minuses. Just in case you didn't think I was being clear on that one, I kind of think that's important if you can't tell. But we say terms of the expression. It says when a term is the product of a number and a power of a variable. Okay, so what we mean is this: the product of a number out front and a variable, or a variable power, like 4 times x to the third, or maybe 2 times x, or x, that's x to the first technically. We say the number is the coefficient of the power. So we say, for instance, over here, this 2 in front of the x, this 2 would be referred to as the coefficient of the variable. Okay, 3 here, we would refer to it has no variable. We say that this is a constant term. Okay, so we refer to this 3 here as a constant because it has no variable term. And then we say, say this 4 here, this would also be a constant because it has no variable. So for instance, when we say terms such as 3x squared, negative 5x squared, when we talk about terms like this, you notice that they both have an x squared on them. Okay, so this 3x squared thing I want to keep in mind here. Keep in mind that we're saying 3x squared is the same thing as x squared plus x squared plus x squared. That would be, hey, I have 3x's squared. And if we were to say this negative 5x squared, this would be the same thing as, quite technically, negative 5x squared, to write it all out and be boring about it. It's negative x squared, negative x squared, negative x squared, negative x squared, minus another x squared. This would be minus 5x squared. But what I want you to notice is this: if we were to combine these, okay, we'd say like, well, this positive x squared would cancel out with this negative x squared, and this positive with this negative, and this positive with this negative. You notice that what we're left with here is this. And we say this would be negative 2x squared. And the thing is, we say 3x squared minus 5x squared, since they have the same variables to the same exponents, they're like identical, then we could have just said this: we really have, in this instance, 3 minus 5 of these x squared things. So these two coefficients here, what we're really doing is we're combining them. And we say, well, it would have been a whole lot easier to say, well, 3x squareds minus 5x squareds would have been negative 2 left of those x squareds. So we say we often combine like terms. And we say like terms are any terms that have the same variable part to the same powers. And again, I just want to mention this: a constant term is anything such as negative 4 or 2. And the reason why is because they don't have any variables. They're always going to stay that value. And yes, constants are always like terms. Okay. So here's what we're going to do. We're going to combine like terms, and the distributive property, which we kind of are looking at here, is what this really is what allows us to kind of just add coefficients. All right. So I'm looking at example number 5 here. It says simplify the following algebraic expressions by combining like terms. And really that's what we tend to do, is say, look at your terms here and say, oh, they like terms. And we notice that these are both y's to the first. So we say, well, 10y minus 15y quite technically is 10 minus 15 y's. Okay, not many people write this out, actually. I was just writing it out for note's sake, but we say, well, 10y minus 15y's, these are like terms. We say this is negative 5 of these y things. Okay, and again over here, we notice here, we say 6m squared minus 12m's to the first minus 7m squared. This isn't a typo. The thing I want to point out here is this: when we combine like terms, I would always start with things, these variables, that have higher exponents on them. And also this: we can only put together the m's squared because they're the only things that are like terms. So this technical written out way, we would say it's 6 minus 7 of these m's squared minus the 12m if we carry this down. But technically we say a positive 6 and a negative 7, that is a negative 1 m squared minus the 12m. And we could just simply write this as negative m squared minus 12m. We don't have to write the negative 1. And then last but not least, when we say simplify, a lot of the times, you might find that you have a situation where you actually have to distribute first. Okay, so a few things I want to kind of comment on. First of all, distributive property says if we have a factor in front of a parenthetical quantity, we're allowed to rewrite this as, say, 3 times x. Now we'd have minus 3 times 2, and we would have the same thing, okay? Minus, we'll write this as 5 times x minus 8. But for now, we say this would be the same thing as 3x minus 3 times 2 is 6, minus 5 times x minus 8. Now, typically, I would have done the 5 also through this set of parentheses first, as well as, or not first, but with the 3 being distributed. But I wanted to point out the 3 first. But now that we've gotten to this point, I want to kind of point this out. We could re-express this as really this, plus a negative 5. Like this here. And the reason why that would be beneficial is because we're distributing a negative here, and that makes a difference. We say 3x minus 6 plus negative 5 times x would be this. We'd say it'd be a negative 5x. And we had a negative 5 times a negative 8, this would give a positive 40. Okay. So now in terms of like terms, we say this has an x to the first and this has an x to the first. We would say, well, how many total x's do we have? Really, this is the question we're trying to answer. And we say, well, 3 and a negative 5 give us a negative 2x. Okay. And we say, well, now do our constants. We say, well, those are always like terms, constants. We say 40 and a negative 6 is really kind of like 40 minus 6. We say this would be a 34. So 2x, negative 2x minus 34 would be the final variable expression that we would end up with here. So one last note I want to make here is this. If we said that two algebraic expressions are equivalent expressions, then we say that they have the same value for all values of their variable. Okay, so for instance, we say the expression 7x plus 4x and 11x are equivalent. And the reason why 7x plus 4x are equivalent is because they mean the same thing. One could literally be replaced with the other one, and they would mean the same thing. Okay. Likewise, if I put an equal sign between these, okay, and this is true for no matter what I plug in for x. I could plug in x equals, 1, 2, 3, 4. I'm always going to get a true statement. Then what I get is what is called an identity. Okay, and an identity is a statement like the one we have here that no matter what you evaluate this for, you're going to get a true statement. So for instance, if we were to put in a 4 for every instance that we have in x here, we would say that we'd really get this. We say 7 times 4 plus 4 times 4 equals 11 times 4, and we'd end up with this expression here. We say 28 on the left plus 16 equals 44, and of course we know that this right here, if you add those up, we get 44 equals 44. So an identity is just what you get when you have two equal expressions like that. It's true for any substitution. Cheers.